So this is G481 homework booklet question 34. Starting off straightforwardly with the define the braking distance of the car, simply the distance travelled while the brakes are applied before the car comes to a stop. It then says other than the speed of the car, state two factors that can affect the braking distance of a car and describe how the braking distance is affected by each factor. So we've got to do two things. We've got to state the factor and we've got to describe the effect of the factor. What we haven't got to do here, which is remarkably generous, is to explain how why those factors have those effects. So that's a bit of a relief. And the other thing, obviously, that I've highlighted to be really careful of is that it does say other than the speed of the car, so I can't give speed of the car. So two I've written down. A greater mass of the car will increase the distance, and a wet, icy or a gravelly road will also increase the distance. Other possibilities would be poor tyre condition, poor road condition, poor tyres, poor road, greater mass, greater speed we can't use, and the other possibilities would be slope. So an uphill slope would decrease the distance, a downhill slope would increase the distance. Other than that, fairly straightforward. Other details that they could have asked questions about would be things like the proportionality, so the distance is proportional to speed squared, proportional to mass, and so on. But they didn't here, and we didn't have to explain anything. But in part C, we have got to do some explaining. Describe and explain how the seatbelts reduce the impact forces on the driver in the accident. So the key thing here is to describe, really. The explain really. The describe isn't saying a great deal because we're told it's a reduction, so there's nothing much less to do in the description, so we've got to explain that. So what's going on is preventing collision with the steering wheel. Maybe that's what they were thinking of with the describing. Everything else we're going to do, we're going to talk about how it's reducing the force, so we've got to talk about what it's reducing that force compared to. So simply we've got to describe how it's going to reduce the force compared with colliding with the steering wheel, with the dashboard, with the windscreen, those other possibilities. And essentially there are two routes we can take. We can do it in terms of distance, or we can do it in terms of time. So this is the work done argument that we've rehearsed lots of times. If we increase the distance for the stopping, we've got a fixed amount of kinetic energy to get rid of. That means we've got a fixed amount of work to do. And if we do that, we can do that with a smaller force if the distance is bigger, because the kinetic energy, which will be equal to the work done, has got to be equal to the work done force times distance. So if this is a fixed number and I can make S bigger, then I can get away with a smaller force. That's one way of doing it. The other way of doing it is by doing it in terms of time. So I'm increasing the time required to stop. I've got to do the same velocity change for same delta v. That means I get a smaller acceleration. Acceleration is v minus u upon t, and therefore if we're using F equals ma for the same mass, same velocity change, we get a smaller acceleration and therefore a smaller force if I can do that in a greater amount of time. So two potential routes for answering that question. We've got a diagram here showing variation of braking distance with speed of a car. That should be a familiar shape. And specifically, in fact, it does show that we've got a proportionality to squared. The braking distance proportionality to the speed squared. So we'll need to come back to that. Car travelling on a level straight road at 20 meters per second. Reaction time is 0.5 of a second, and it asks us to calculate the thinking time. So, thinking distance. Thinking distance is simply speed times the reaction time. I've got a speed, I've got a reaction time, multiply them together, I've got 10 meters. Hence, it says, which means I'm going to have to use that answer, determine the stopping distance of the car. Well, stopping distance right from the beginning is braking plus thinking, or thinking plus braking, and I can look up from the graph that at 20 meters per second, here I go, 20 meters per second, the braking distance is 30. So to get the stopping distance, I need to add the 10 that I've calculated to the 30 that's come from the graph, and that'll give me an overall stopping distance of 40 meters per second. Now it gets nasty. It asks us tells us that in 34.1 the braking distance is proportional to the square of the speed. That's a key bit of information. The braking distance is proportional to the square of the speed. You should know that, but they're telling you that because without it you're going to be absolutely stumbling on this question. And you're asked to determine the braking distance when the car is travelling at 32 meters per second. Now, if I've told that displacement, the braking distance, is proportional to the speed squared, I can rewrite that as displacement is some constant times v squared. Now, we've already looked up that at 20 meters per second, when v is 20 meters per second, s was 30 meters, so k would be s divided by v squared. So there's the 30 meters divided by 20 squared, and it turns out to be 0.075. Now I can then use that same equation, s equals kv squared, with v equals 32. There's the k I've worked out, 0.075 times v, 32 squared. Put that through your calculator, you should get 77 meters. So that's one approach to doing that, and always the case when you're doing proportionality. Often one way of doing that is to work out the constant of proportionality. Another way is to look for simple multiples in the information, and we're asked for the speed at 32 meters per second. Obviously the problem is that in the graph only went up to 20 meters per second, so I can't just read it from the graph. But hold on, one simple one to look at would be to look for 16 meters per second. And looking at that, 16 meters is going to be meters per second is going to be 2 squares in, which is just a hair over 19. If I come up, it's this line here. Ooh, if I can get that accurately, it's this line here, and you'll see just in there that's just a hair over 19 meters per second. So at 16 meters per sorry, just over 19 meters. At 16 meters per second, I'm going 19 meters. Okay, so that's information from the graph. Possibly I could argue it's 19, say, and a quarter, but 19 is perfectly reasonable reading off. So if I go to 32, because it's a proportional, because displacement for braking distance proportional to the speed squared, I don't need to just double that. I need to multiply it by that factor 2 squared. So I get the displacement at double the speed will be 19 times 2 squared, and otherwise times 4, which is 76 meters. That's the number in the mark scheme. Now I did say that actually looking really carefully at the graph we could see that was a hair over 19 meters, maybe 19 and a quarter. Of course if you went with 19 and a quarter times that 4, 2 squared is 4, you would end up at 77, which is the same thing we got over there. So whichever way you do it does all tie together. So that's G481 homework booklet question 34.